Good afternoon, everyone. This is Carlos Morillo. I'm going to be your host in this webinar. Thank you again for sharing this time with us. Today we have an FTIR microscopy webinar. Dr. James Burgess is going to be presenting. I just want to remind everybody that later we are going to send the slides and the recording. So let me talk a little bit about James. Dr. James Burgess obtained a BS in chemistry at the University of West Georgia, performing ultra-high vacuum and environmental chemistry research. James earned a PhD in analytical chemistry at the University of Alabama for surface science and material research, using IRAS, that is the infrared reflection absorption spectroscopy. And these techniques were performing vacuum system. Also, he studied Raman microscopy of ferromagnetic perovskite and fabrication spectroscopy of carbon materials. He also taught 2 years at the Georgia Southern University while completing his dissertation and applying for a postdoctoral position for the National Research Council at the Naval Research Laboratory, and his work at the NRL involved functionalization of graphene, including first reported fully fluorinated graphene and functionalizing micromechanical resonators. After NRL, he was project manager for 2 FTIR projects involving the functionalization of chemical pre-concentrators for cBRNE detection. Next, he was FTIR and Raman application, focusing seminar, demonstration, experimental design and instrumentation, instruction to meet customers' needs, and his skills include knowledge and experience in multiple analytical techniques, surface science and method, and application of Raman and FTIR. James' research has been awarded 2 patents, 5 research rewards, 2 book chapters, 3 grants, 12 manuscripts with 1,500 citations, and 40+ poster presentations. So with you, I just want to let James start his presentation. Thank you.
I think I need to truncate that intro. It was a little, I didn't realize I wrote that much. Hello, so thanks for signing in today. Like Carlos said, I'm going to be talking about FTIR microscopy. A little bit about JASCO. It was founded in 1958 by Fujioka and Tominaga, who actually won the Nobel Prize for quantum electrodynamics alongside Richard Feynman. We have 6 PhD scientists on staff, and 2 of which, Carlos and I, are the vibrational spectroscopists. So we do Raman and FTIR. JASCO has a far-reaching range of spectroscopic instrumentation. We have IR, Raman, circular dichroism, both electronic and vibrational, IR microscopy, UV vis, and fluorimetry. And we also have a line of chromatography products as well. A little bit about our FTIR FTIR products. For the microscopes, there are 4 different microscopes. There's one with a room temperature detector, and I'll be talking about detectors later. 2 with MCT, and then the 7200 has a linear array detector, and I'll be talking about detectors, like I said later. An outline, there's an introduction. We'll talk about theory and instrumentation. I'll be fairly brief on that. Sample preparation, the different techniques that are available with the microscope, complementary microscopic techniques, so techniques that are not FTIR but have different utility in seeing the sample. Also, I'm going to go over the imaging software that we have and talk a little bit about chemometrics there as well. So first up is the FTIR theory and instrumentation. So I went through this. There's a prior talk I gave on basics of FTIR, and I highly recommend you go download it. So this is a truncated version. So infrared transitions, the infrared excites a ground state into a vibrational excited state. It does this by changing the dipole moment, or when it does this, it changes the dipole moment, which causes a bond to either relax or contract. And that's where you get the vibrations. The number of vibrations in a linear molecule is 3 times the number of atoms minus 6. So you can imagine the more complex a molecule is, the more complex its spectra is going to be. This is an example spectrum of isopropanol. So you can see these stretches and bends show up around the same region for all different molecules that have the functional group. So this has the functional groups OH stretch, CH and CH3 stretch, CH and CH3 bend, OH bend, carbon-carbon stretch, and COH bend. So as I said, one of the advantages of IR is being able to identify functional groups. So a alkane molecule is going to have a CH on an alkane molecule is going to have stretches around 2800. Now on alkene it'll be a little higher, and with the alkyne it'll be even higher. So knowing this is a correlation table, knowing this allows you to see what bonds you have. Sometimes that's important for for some sorts of reactions when you want to monitor reactions. So you can see a double bond O, for example, turn into an OH. A bit about the interferometer. So the interferometer is how the infrared instrument generates signal. So there's a source that hits a beam splitter. Some of the light goes to a stationary mirror, and some of the light goes into a moving mirror. Then it gets recombined and goes into the detector. So this is an actual moving mirror assembly for one of the JASCO products. And you can see it actually has a retro reflector on it. So if there's any kind of jitter, any time of vibration, it's not going to go out of alignment. The spectra are, the moving mirror causes a destructive or constructive interference in the molecule as it moves from its 0 position to out of phase. These data points are taken at each crossover of the timing laser. So the timing laser is important in that it gives you the accuracy that you need. So a laser that's not a Heaney laser is not going to give you as good, a good reliable frequency. So that means your frequency on your infrared's not going to be as good. Then next, the computer this is the signal from the detector. It goes through what's called a Fourier transform, and it's converted into a single beam spectrum. So it goes from time domain to frequency domain. And this is a diagram of JASCO's FTIR bench. So the light comes through, gets reflected, goes through the beam splitter, gets reflected again, and then it has a choice. It can go through the bench itself and into a detector, or it can go out of the instrument. So this is where the FTIR microscope would be. So this is the generation of your interferogram, and then your actual spectra and your sample are going to be external. So these are some of the detectors that are possible with IR microscope. So we have photodiode for near IR, and then there's the room temperature detector, and then MCT wideband is here. You see it goes from 450 to 12,000, and that's really good enough for most applications. The MCT detector is about 100 times more sensitive, or a few orders of magnitude more sensitive than the DTGS. So a linear array. So each element in a linear array is a MCT or an N-gas. And the N-gas is for near IR measurements. So you can actually, with a linear array, you have 16 in a row. You have 16 in a row, so that means each scan going up is going to be 16 at the same time, as opposed to a single point detector, which is what you have with the DTGS and the regular wideband MCT. So this takes 16 times less, 16 times fewer, 16 times the sample over the same amount of time as one. So you can imagine this is really good for faster scanning, and it also gives you better spatial resolution as well. IQ mapping, this is unique to JASCO, and the way it works is that light comes through a steering mirror and is reflected back onto the sample. What this allows you to do is actually that scanning mirror, as it moves, it's going to move where the instrument is getting its signal from. So you can without moving your objective, you can still take a map. One of the things it's very useful for is samples that may deform or shift in contact with the ATR. So when the ATR hits it, it may not be, when you move the ATR, it may not be in the right spot after it shifts. So one of the features in most of the models, you can get manual stages, but or automatic X, Y, and Z stage. And this allows you to do a map taking several data points. Another feature that's nice is the Linkum stage. This is the Linkum stage, and this is the stage controller. This can be used to bring your samples down to 196 or negative 196 or up to 600 Celsius. It's a different one for each region. For cooler is going to be different than the heater. If you have samples that either interact with the atmosphere or if you've got really weak signal, it's very good to use a purge stage. So purge stage, just as it sounds, is a purge box built around the stage. And I actually really like this design. It's compared to a lot of the other ones, it's a lot more fits flush to the instrument as opposed to some of the others. And then if you're looking at really, really low signals, you can actually have the vacuum bench and then the evacuated stage area. So some about sample preparation. So for transmission spectroscopy, what you do is you ground 3% of the samples into KBR and then grind them to fine powder and then press using a high pressure hydraulic press. You can press the KBR until it's crystalline. For a liquid, it must be non-aqueous because you can imagine putting water on KBR would ruin the KBR window. And then a drop can be placed on the KBR window and the Z-axis would be right above the KBR window. However, the best, the easiest to use is a diamond anvil cell that has 2 diamond windows. This housing comes apart. So these are thumb screws. When you unscrew them, you can take the top off and it has a diamond on one side and a diamond on the other. You can put the sample onto that diamond window and then you crank the thumb screws as tight, fairly tight, so that you know the sample is compressed, so it's IR transparent. Larger samples, flat samples, double-sided tape can be used on. A resin is really good for cross sections or really small samples that would not stay up otherwise. And then the last one is silly putty or rubber tack. They're really good for if you've got a larger sample that's uneven and it's at an angle, you can actually put it on the tack and change the tack around until it's flat to the surface, flat to the objective. Another good thing to have is the slicers. So JASCO has what's known as a Slice Master series, and that includes a vertical slicer, an angled slicer, or the multi-angled slicer, and the tablet slicer. The hands down, probably the most popular one is the multi-angle slicer. So that way, especially if you're in a quality control lab, you're not locked into one orientation. However, if you're doing a lot of tablets or plastic pellets, you could use the tablet slicer as well. So some techniques, I'm going to go over several different objectives and the techniques and some examples. So the first I'm going to talk about is reflections. Fairly straightforward. It uses what's known as a Cassegrain objective. So there's a secondary mirror and a primary mirror, and the light is collimated and comes down to the primary mirror and then is reflected onto the secondary mirror, onto the sample, and then that light's reflected back into the detector. So here's an example of reflection for a malignant tissue sample. So this is the image, and this is the actual IR map of the sample. So the peaks on there from 1647, so it's the amide peaks, are being monitored. So you can see where the protein is in that cell, that cancerous protein. Another example is a tablet, and these images are actually acquired using MCA, and I'll talk about that later. And if you look at the left, this is the distribution of the API, and this is the distribution of the pellet. So you can see of the additives. So as you can see, it's pretty well distributed through the sample. The next technique I would like to talk about is the transmission. So just as in reflection, there's a Cassegrain objective at the top that takes collimated light in, focuses it down to the sample, and then the addition of another Cassegrain called the condenser, the light goes through and it gets collimated again to go to the detector. So it's very close to reflection, except it's going through the sample instead of off the sample. So this is an example of a cross section of a chip bag. As you can see, there's multiple. You can see multiple lines visibly, and each one of those, a sample was taken. So ADE. So there's that one, and that one are one polymer. Then B and C are separate polymers. Another example is a multi-layered film, and you can see where this impurity in this film, the impurity is coming from cellulose. So it's a quality control application. Next is attenuated total reflectance. Again, you have light bouncing off of a primary mirror onto a secondary mirror, and it hits a ATR crystal. So it's attenuated total reflectance, the ATR crystal, and then bounces back through. The crystal is in contact with the sample. The penetration depth of ATR is fairly low. It's anywhere between 800 nanometers to 1.5 microns. So these are three examples of different ATR objectives you could have. So this is diamond, this is zinc selenide, and this is germanium. And I'll talk about when to select what a little bit later. So the refractive index is fairly low compared to the germanium for the silicon, the zinc selenide and the diamond. What that means is that this is going to have a lot lower penetration depth. So this is an example of a multi-layered sample that was taken with this is the wide MCT. So this is 400 by 400 microns, and this is the standard ATR, which is with an area of around 60 microns. And what it found, this is a good for the wide angle. It's a good for surveying and finding the spot on the sample that you want to see to investigate further. So what was found was that it was a cellulose, and there was some calcium carbonate alongside kaolin in the middle here, and then the last one is the polyethylene. So some application examples for the ATRs. So this is where germanium really is the best one to use, because dark samples like this tend to have weak weak IR signal, and it actually absorbs too much of the light. Germanium's got a lower penetration depth, so you have less absorption. So these are the two different ones. You can see that there is a marked difference between the normal rubber and the deteriorated rubber. And these can be taken with a subtraction, and then you can actually do a library search and find out what your unknown, what the difference is. Another novelty that JASCO has is the clear view view through ATR. So in a normal ATR, the crystal is raised and the light to visualize the sample, and then it's lowered to characterize the sample. With the ATR side, the view through ATR, the light is actually focused on the crystal, and you can take an image. So both these steps are happening simultaneously. And of course, you can only do it on clear ATR crystals, so it's on diamond or zinc selenide. So some examples where you really want this. One is a fiber sample. So if you've got a fiber and like I said, the ATR is in contact with the sample. Well, if you poke your thumb onto your carpet, you can tell that the fibers move when you put any kind of contact on it. So what is really useful is that you can have the ATR in contact with the sample, then take your picture, and then you can decide where you want to take a spectrum. So you know it's at the same spot that you put down is going to be the same spot that you're measuring. Another good example of why the clear view is good is this is a PMMA particle in machine oil. So you can imagine if you've got a solid in a liquid, then when you put the ATR down, you may move that solid to a different spot. So if you took the scan, if you just looked at it and then laid the ATR the ATR crystal onto the surface, then it can actually move the particle. This way you have the particle will still move, but it'll move and you'll be able to see where it moved to and actually take a spectrum of where the particle is. The WG objective is, I really like this. It's 400 by 400 micron sampling area. So if you do that in conjunction with IQ mapping, then you can do a very large area without moving the crystal. So again, every time you lift the sample up, you're causing a disturbance to whatever you're looking at. So if you've got something that's got adhesive on it, say, you don't want to lift the ATR up and then go to another spot because the adhesive will still be on your tip. So you'd have to clean it between each one. But if you have the ATR crystal on your sample and then take a spectrum, a map without moving your ATR, you don't have to worry about cross-contamination. So this is an example. So again, this is a small particle that's been imaged. So there's some of it's butadiene rubber. The rest is silicon. The silicon's acting as a filler in this molecule, in this particle. So with the ATR crystals, some of them are more fragile than others. Diamond's the most robust, but zinc selenide can deform and germanium can crack. So it's good to have a pressure monitor sensor. So you put the pressure monitor sensor onto the stage, and then you set what pressure you want it to go to. And another thing about the pressure sensor, you could actually do experiments at different pressures to see if it has effect on the sample. So a grazing angle objective, it's fairly similar to what you'd use as a grazing angle accessory for an IR bench. It's got a very shallow 70-degree incidence angle, which allows you to see films down below 2.5 microns. The caveat to this technique is you have to have it on a metal surface. So say gold is probably best. You have a gold plate, and you can put you can put the polymer on the plate and then see. And then this also gives you very, very weak signal, so you need a linear array or an MCT detector. So this is often used in conjunctions with polarized light, the polarized IR, because you can find out orientation information. So you know this is oriented at 0 degrees polarized, and there's no signal hardly at 90 degrees polarized. That's because it's in the it's in the plane. Then the last technique I'm going to talk about is time resolved spectroscopy. So this example is an LCD element. This is the it's using a linear array, and the bench is set up for step scan. In other words, the mirror moves. You take a spectra, the mirror moves. You take a spectra at a really, really high rate. And for this to work, you need a sample that's reversible. And in the case of liquid crystals, it is. So as time goes on, and it's pulsed, so there's a pulse of radiation or voltage to the LCD, you can actually see the orientation change. So you have 19 milliseconds, there's not really any kind of orientation. Then 21 milliseconds through 40 milliseconds, you get a lot more like the whole surface is oriented, and then that slowly dies down. So you know after you fire your LCD monitor up, it's going to take about 60 seconds for it to cool, milliseconds. So I'm going to talk a little bit about software. So this is the software that JASCO uses. It's called Spectrum Manager. And on this pane is for different scan speeds and resolution and everything else. So this is where you set that. So this has to do with more of the bench. And this is the microscopes. This is where you change aperture. This is where you do most of your microscope side of data collection. This is a live spectrum of where the sample is. And then you can take this and you can actually map, and you can start the map before you're done and actually see it populate as it goes down. We also have analysis software that can do a little bit more than the data collection software. So this is a spectra that's on the surface. It looks like an amide, looks like a biological molecule on the surface, and you can see that the different biological materials actually collected around the numbers, the raised numbers. So you can create a false color image if you know what peaks you want to look at. So this is 1600. Then you can have the visual of the sample, and then you can do a 3D plot. You can have a 2D heat map or 3D plot. So now I'm going to go into a little bit of chemometrics. So there's a couple that we have that are variants of Beer's law. So Beer's law is absorption is equal to molar absorptivity times path length times concentration. The classical least squared compares the absorptivity to one of a known concentration. The inverse least squares does the absorbance of multiple spectral features. So this is looking at multiple peaks, and this is just looking at one. And I'm just going to go over principal component analysis. So most of these we don't necessarily use on the microscope as much, but principal component analysis is pretty important for the next slide. So it reduces the variables to principal components. So it scores and groups them. So in this case, you know, all the MAs are all grouped together, the APs grouped together, MDMAs are grouped together. So what that means is that the software is recognizing, it found these groups and recognized it, then labeled based on search. So multivariate curve resolution, this is the one that's really interesting. So what you can do with this is what it does is PCA, and then it takes the grouped samples and calculates their percent. Then you can do a library search, and it will library search for the different spectra, and then it will label each spectral component. It will label it with the library search name. All right, so some complementary microscopic techniques. So one example of a complementary technique is actually fluorescence. So if you have a sample that's hard to see, doesn't have a lot of contrast, and it fluoresces, you can actually get a better picture with the fluorescence unit. And you can do different excitation and emission wavelength, so to find the optimal fluorescence. Another is differential interface contrast. So if you have samples that are clear or have a really low contrast and are difficult to see, you can use this to really get the pictures to pop. So visible polarization. So if you've got a sample, in this case is a good example of, it's really hard to see that there's a difference, like there's more than one different polymer on this. But if you do polarization, you can actually see the light. You can see that there's 1, 2, 3, 4, 5 different regions of interest. Next is IR polarizers. I kind of briefly hit that with the reflection, the grazing angle. So what you can do is actually look at the ratio of two peaks, in this case 973 and 1378. You look at that ratio of the two, you can get some information about what direction. So this is in plane polarized detection. So you don't get a lot of signal there, but you get a lot more signal out of plane. So you know the orientation of the sample. Another feature that we have is what's called a sharing holder, or the IQ frame. And how that works is that if you've got a sample that either A, you want to keep going back to, or B, if you want to switch from IR to Raman, you can put the sample you put your slide onto the stage, and then there's these little tick marks that will give you position. So if you know the position of this, the computer saves the position in the software, and it will go back to that position every time when you want to stay. And finally, but not least, the Raman microscopy. So Raman is often said to be complementary to FTIR, and it's good for samples containing water, inorganic compounds, or carbon materials. So an illustration of these actually being complementary is this on the left is IR, and this on the right is Raman. So you can tell the spatial resolution on the Raman is much higher than the spatial resolution on the FTIR. And that's by nature of the Raman signal is coming from a smaller wavelength than IR signal. So you get better structural information from this. However, this impurity doesn't show up on Raman, and it shows up on IR. So there's a lot of compounds that don't show up on Raman, but do show up on IR, and that's the basis of wanting to have both techniques. So in summary, FTIR is a valuable tool to identify and quantify compounds. It's useful for multi-layered films. We talked about a few of those. Surface composition, we've talked about that. Inclusions and computational analysis. FTIR, the objectives are reflection, transmission, ATR, and grazing angle. The clear view with the IQ map allows a large area to be scanned without moving the stage or objective. The common detectors are room temperature, MCT, and linear array. And then depending on the sample, DIC, fluorescence, polarization, Raman can be used to visualize a sample, and chemometrics are a valuable tool to determine the composition of a sample. Sorry. We have another webinar coming up on June 2nd, which is going to be HPLC. And some of our past webinars that you can still access, just ask us, we can get it to you. Vibrational circular dichroism, FTIR theory, instrumentation and techniques, circular dichroism, FTIR microscopy, Raman microscopy and imaging, SFC, supercritical fluid chromatography, and fluorescence. And we have ebooks, several ebooks, and the knowledge base. The knowledge base is pretty neat because it's a storehouse of abstracts from papers that use JASCO. So you can actually see straight from the horse's mouth what the data is going to look like. All right, well, that is it for me.
Okay, thank you, James, for that very nice presentation. I just want to remind everybody to in the coming days you are going to be receiving the slides and a link with the recording. From now we are going to start taking questions. You can write them in the question box, so either James or I we are going to answer your questions.
Hey, Carlos, I can't see questions.
Okay, I will send it to you.
Yeah. What is the resolution for the FTIR microscope? Are we talking spatial resolution around 3 microns typically? Spectral resolution's going to be, what is it going to be? Be determined by the instrument you have attached. So spectral resolution, you can do, with the 6600, you can do down to 0.4. So you can get pretty good resolution. How does the Raman spectrometer solve the fluorescence background noise? It depends on there's a few different ways you can get around it. One is change the wavelength. So if you do 1064 nanometers, then you usually get rid of fluorescence. Another is if it's the fluorescence not bad, we have a really sophisticated fluorescence removal as part of our software. There's other things you can do. You can actually, if it's not the principle what you're wanting to see, sometimes you can actually burn the part you don't want. So you hit it with a high intensity light, and then you can get rid of it.
Yeah, there are more questions coming.
Yeah, I know. I'm trying to get to them. My screen looks funny. What is the sample size for FTIR, and can it give a percentage of API excipients? Yes, it can. Sample size, like I said, its spatial resolution is 5 microns, so as long as you're bigger than 5 microns, it's fine. I was wanting to ask, is it possible to determine crystalline defect from IR? Yes, that's one of the uses for it, especially if it is something like titanium oxide or any kind of defect, really. I think I showed one that had an inclusion. That was the cellulose inclusion. Does the microscope only operate in ATR mode, or can it also do reflection transmission Why would you do one mode over the other? ATR generally gives you pretty good signal. Reflection's easier to use, but if you've got a sample that doesn't reflect well, then it's better to use ATR. Transmission is really great if your sample is thin enough to where it can go through. It doesn't, we're talking on the order of like 10 microns, 50 microns. It needs to be to do transmission, but it gives you very clear signal. So long story short, ATR is good because it's got multiple uses. Transmission is the best, but it's the hardest to get a sample for. And the reflection is good if your sample is reflective enough. Can it be used for trace analysis on equipment surface, as in the case of cleaning validation? So it depends on the size. It can do, and what you mean by trace. So if you're looking to just at a reflective coating, you could do a reflection measurement and go across to see if it's works. But the piece of equipment, I mean, it's going to be probably not going to fit into the microscope. So it may be better to do reflection technique. Is Raman better for crystalline structures or IR? For example, nickel phosphate structure. With IR, you'd need to get down to like 400 wave numbers probably to see it. And in that case, you can see the crystal structure with IR. That being said, it's easier on Raman to do most oxides, show up better in Raman than it does in IR for metal oxides anyway. Was it Lincoln stage for temperature control? Yes, it was. Can it be used to track current curing of an adhesive or polymeric system? Yes, it could. That's actually a really good use for it. Depending on how you're polymerizing or curing, most curing I've seen has been C double bond O as part of the reaction, so you can actually watch it over time, so you can do time course measurement. Thank you for the webinar. Thank you. Is it possible to quantify the fat content of fried products using FTIR? It depends on how much moisture there is. So it's going to be hard to do mid-IR on something with water, and most of those have a decent amount of water in them. The best thing to use is near IR, because near IR is sensitive to water, and you're looking at fat content, which is going to be large anyway. So that's really, I would say, go near IR and probably not worry about the microscopy, although the FTIR microscope can be used in the near IR. On what basis does the software run chemometric analysis? Not sure. Carlos, you know that one?
I think the question is based on which algorithm is using, and actually you talk a little bit about that. And JASCO software have the suite for the chemometrics have the 5 different algorithms. The one that you show is CLS, PLS, PCR, PCA, and MCR. So we have a different algorithm to do the chemometrics. I hope that I answered the question.
Is there any problem that you can think of if the peaks in the spectra disappear in the remeasurement? That's not a good thing. It means there's, it could be that some of the sample, like if the sample is stuck to the ATR, I guess that could do that. But yeah, in the remeasurement, if it's not there, either your first spectra was wrong or your second spectra, the system changed. So it's possible, but it's not possible without a spectra change in the sample condition. Does a microscope only operate in ATR mode? Or can it also do reflection transmission? It can.
Can I read one? Yeah. There is one question is really good. the polymer cross-section you show where it goes in transmission, and the answer to that is yes. How thick were those slices, and were those slices prepared with the JASCO slices? If you're familiar with the transmission measurement, you should be aware that it is very easy to saturate the detector. So you have to make sure to make those slides as thin as possible to don't saturate the detector. And actually, if I remember well, we are talking about in the order of 5-10 microns. And the way to cut those samples are with the slide master. And actually, we can graduate the amount of the slides that we can do with the instrument. And of course, after that, we are going to do some pressure with in a KVR window. So yeah, the question is really good because for sample preparation is critical, and we have the accessories to create those slides.
What is the best method to use to analyze rigid, irregular surface specimens? Depends. If it can reflect, I'd go with reflection. Otherwise, probably a diamond ATR, just so that you don't hurt your sample, hurt your crystal. But yeah, reflection if you can. Can FTIR be used to quantify the phthalates in a ROHS limit of compliance? I'm not sure what the ROS limit of compliance is.
Let me answer that one.
Okay.
The ROHS, or some people call it ROHS, is the directive from the European Union. And with the passage of the time, we have like several environmental restrictions. There are elements that they have been banned from electronics, and now the most recent in 2015, and actually they came into place, I think, in 2019, is the banning of different phthalate materials. So what is DAHP, DBP, BBP, and DIBP. So those 4 phthalates are now controlled, and they are restricted by ROHS, and now they can be measured using different techniques. But using FTIR is very fast. So actually, for the person who is asking this, we just came out with an application note, and if you want, we can send that to you. And we are measuring the different phthalates and the content in different materials. We work with a Japanese company. The name is Kankyo, and we developed a methodology using JASCO instruments to measure the amount of phthalates in different products, especially for the main focus is in toys to restrict this type of polymer materials.
All right. So what is the thickness requirement for multi-layer structure? So it depends on whether you're planning on doing transmission or reflection. If you're doing the smallest size you can usually see is around between 2.5 to 5 microns. So it'd have to be on that order to distinguish between the layers. And that's with a cross section. Can we use nanoparticle powder material to measure in FTIR? Yes, and I would actually, you don't really need a microscope for that. You can actually just use a regular ATR. Is it possible to get cross-sectional image, and if yes, what is the resolution and depth? So it's really, honestly, you'd probably be better off with Raman for that if you're going into the sample. because with Raman, it's confocal, meaning it can take a really thin slice of the material and then go up and down and to get a depth profile of the sample.
I kept sending you a question because the question keeps coming, so I'm just trying to send it to you. But I guess that there is some delay.
Yeah.
Well, there are several questions asking about the Z scans, and I just want to make the difference between the two instruments, Raman microscopy and the FTIR microscope. The last week I was presenting about the Raman, and the Raman is a confocal technique, so we can do the mapping in the Z direction, so we can have a 3D image and the 3D mapping. If that is not the case for the FTIR microscope. I'm just answering that because there are like 3 or 4 questions about the same.
I wonder if I'm going the wrong way. Oh, yeah, I was going the wrong way. Reflection at 2 interfaces. Is there a way to avoid this? I mean, you might be able to aperture down a little bit.
James, can I answer one question that the same person made the question and then asked me again to read the question? His second comment was like, please read my question. So it's a question about microplastic particles, and he's asking about the different techniques, either FTIR or Raman. I have to say both techniques are vibrational molecular techniques. Both can be used for microplastics. But as you are mentioning that these particles are collected from water samples, there are some cases that the microparticles that can be collected in a freshwater body or salt saline body water, not all the times all the particles are microplastics. So some of them can be different materials. So of course they are going to be detected with FTIR. In the Raman, you are going to have that station that you can measure some of those inorganic materials. Anyway, we have also an application note for microplastics, actually with both techniques. And if you want, I can send you that. And you will see the difference. And of course, yeah, we can determine the composition of these, identify what is the material. And the question is, the particles are really small. Well, really small, we can talk, a microparticle can be sometimes the size of 5 microns. So it can be either measured with the FTIR microscope or the Raman. Okay.
Okay.
There is more people asking about access to past webinars, and when you are going to receive an email with the slides and recording. In that web page, you are going to find the previous webinars. Okay.
Would FTIR characterize amorphous polymeric matrix? Yes, it should do a good job of it. That's pretty standard. How can we determine crystalline defects from IR? You may be able to see some. There's things like peak shifts that will become apparent as it's as say there's some sort of deformation of the crystal or a crack or whatever. edges will show up in IR. Again, this is usually the crystalline defects I would go towards Raman on, especially if it's, I'm assuming it's inorganic crystal. But IR can do some, and Raman, however, you get sharper peaks, so you can see the peak shifts better, and that's what's going to tell you about your defects. So how can we analyze extra peaks in the IR spectrum? Sometimes there are peaks which you might not match with any kind of reported bonds. Should we repeat the tests or what? I mean, I always repeat tests first just to see if I'm going crazy or not. However, the bonds may be, if it's a crystalline material, may actually be from the crystalline structure. But yeah, I would definitely redo it. What is the penetration depth? It's on the order of a few microns. Okay. The Lincoln stage, a question about the Lincoln stage. It was a Lincoln stage for temperature control, and it can track the curing of adhesive or polymers. That's actually one of the standard uses of IR. Can we use the temperature dependent monitoring for silicone adhesives? As long as it's within that temperature range, you can. So as long as it's 600 degrees or lower. So should FTIR be?
Yeah, go ahead.
Should FTIR be used in clean room or a clean environment? You shouldn't necessarily be that important. You do want it to be humidity and temperature controlled, so you don't want it open to air because there's a lot of optics that are moisture sensitive. Clean room would be overkill. You can use it in a clean room, but it doesn't need a clean room. And if you're worried about any kind of environmental effects, that's when you'd want to get a purged housing, a purged stage, purged or evacuated. But
James, there is one question. It had been repeated several times. He is asking if it's possible to do the lithometry measurement using this system and an attachment for variable reflectivity measurement. I haven't heard about this.
It's not impossible. So when you do reflection, sometimes it can cause you get the different peaks. It looks like a sine wave superimposed on the spectrum, and the distance between those peaks is going to be related to the distance of your thickness of your film. So it's not impossible. You need films that are on the order of 5 microns. So they have to be pretty thin films, but it is possible. It's just not, I mean, if you had samples you'd want to send, we could run the samples and they'll let us know, but it really needs to be something on metal, basically a film on metal.
I sent you a last one. There are more. Yeah.
Oh, so you're sending me the questions?
Yeah, I think that I sent you all.
Okay. So we've gone through them?
Yes.
All right.
Okay. Well, thank you, James. Thank you, everybody, for joining us today. You will receive the link with the slides and the recording for today. And next week on June the 2nd, we have Mr. Tom DeFilippo with the SPLC detectors talk. So this is related to our chromatography instrument accessories. So please feel more than welcome to sign up. Thank you.
All right. Thank you, everybody.